Some 1990s automatic transmissions outlast the engines they pair with. That sounds extreme, but people still driving these cars past 300,000 miles know it's true. If you plan to buy a 90s car that you want to actually drive for years, knowing which transmissions were engineered to survive and why can save you thousands. Today we'll rip the hood off the myth, get into the nuts and hydraulics, and show the practical checks that separate a long-term keeper from a ticking wallet drain. First, a quick primer so the rest makes sense. A 90s automatic is not a black box of electronics. It's a hydraulic machine built around three mechanical truths: the torque converter, the clutch or band packs, and the valve body that routes fluid under pressure. The torque converter multiplies torque with a fluid coupling and a lockup clutch. Clutch packs provide selectable gear ratios through stacked friction plates. The valve body controls which clutch pack is pressurized. All of this relies on a controlled pressure circuit, reliable sealing, and a predictable heat path. The secret to long life is how these parts handle force distribution, heat, and material fatigue. Let's start with one of the most common survivors, the GM 4T60 and its later sibling, 4T65. These boxes were everywhere, which mattered for two reasons: lots of design iterations and a huge aftermarket for parts and knowledge. What makes them tough is a combination of engineered redundancy and simple mechanical load paths. The lamella design in the clutch packs uses slightly larger friction surface area and a thicker steel backing plate, so the contact stress per square millimeter is lower than on many compact designs. Lower stress per area reduces localized wear and delays clutch glazing. The planetary gear sets run on robust sun and planet gears with broad tooth engagement zones, which spreads the torque across multiple teeth instead of concentrating it on a narrow patch. That reduces bending fatigue in the gear teeth over hundreds of thousands of miles. Hydraulically, the 4T6X family uses a pressure regulator and a relatively conservative line pressure map. In plain terms, it does not push clutches full tilt at the first sign of load. That softer pressure profile gives smoother shifts and less shock loading on clutch surfaces. Any design that prioritizes gradual pressure application tends to trade a bit of crispness for longevity. And that's exactly what the 4T60/4T65 did. On the service side, these transmissions are forgiving. Filter and pan access is straightforward, and the magnet placement in the pan collects large metallic debris before it can circulate and score valve body passages. Those small design choices add up. If you find a 4T6X with regular fluid changes, you can expect it to go far. If you find one with burnt fluid and metal on the magnet, assume clutch wear is already advanced. Next up, Toyota's A340E and A343F, the companies people point to when they mean buy it and forget it. Toyota prioritized seal and material selection and conservative thermal margins. Seals in these units used a slightly more advanced fluorocarbon compound in later iterations, which resists swelling and shrinkage across years of fuel and additive exposure. The torque converters were sized with slightly larger turbine and stator diameters relative to the engine's max torque. That gives lower slip speeds at cruising torque and reduces the shear heating inside the converter. Lower shear means the fluid and friction materials age slower. The hydraulic control strategy in Toyota's design is intentionally conservative. Shift timing favors cooler operation and limited overlap between clutches. Less overlap reduces slip events where two clutch packs partially engage against each other, a common source of wear and heat. Toyota also engineered the lubrication flow with clear channels to critical bearings and the sun gear carrier, so localized thermal hotspots are less likely. Those engineering choices are subtle but powerful. The trade-off is that Toyotas often feel less aggressive at low RPM shifts compared to sportier boxes, but they survive because they were built to be unexciting and reliable. European cars from the same era often used ZF gearboxes. The 4HP and 5HP families are classic examples. On paper, ZF boxes are technically superior: tighter tolerances, more sophisticated pressure regulation, and quicker solenoid-actuated control. That precision yields better efficiency and crispness. The downside is sensitivity. Small deviations in hydraulic pressure or fluid cleanliness can upset the whole control strategy. ZF valves and valve body channels are narrower, and the pressure regulation system uses more feedback loops. When everything is clean and calibrated, these transmissions run far and smoothly because the clutch engagements are precisely timed, and the converter lockup behaves optimally across a wider range of conditions. But when sludge, varnish, or an underperforming pressure regulator enter the equation, the tight tolerances work against the transmission. Solenoids misfire, small leaks in pressure paths cause slipping, and electronics try to correct behavior that should be hydraulic. So ZF longevity is a high-reward, higher-risk proposition. Exceptional life if maintained, painful bills if neglected. Now let's compare these designs in terms of how they distribute force and manage fatigue. Imagine torque as a wave that passes through gears and clutch surfaces. In a robust design, you want that wave to dissipate across wide surfaces and multiple load paths. GM's approach spread torque through broad gear mesh and thicker clutch plates, which reduces peak contact stress. Toyota relied on conservative hydraulic timing and material chemistry that resist thermal breakdown. ZF focused on precise control so that contact events are well-timed and efficient, but at the cost of requiring clean fluid and working electronics. Material fatigue also matters. Clutch friction materials age from heat and abrasive wear. If the friction pads are thinner or the backing plates are flexible, you get localized hotspots and early glazing. Modern replacements or improved aftermarket friction compounds can dramatically alter life expectancy. Some builders intentionally use a slightly more aggressive compound for performance, but the side effect is shorter life. On the other hand, a slightly softer compound with higher thermal capacity will accept more abuse and self-cool marginally better. It's not glamorous, but friction chemistry is as decisive to longevity as gear metallurgy. Heat is the other silent killer. Every conversion of mechanical energy to friction creates heat. If the thermal path, oil passages, coolers, and pan conduction is compromised, the whole system ages fast. Toyota's invested in robust cooler plumbing and inlet screens that reduce aeration and preserve oil film. GM designs often relied on service-friendly coolers, which meant owners could replace or flush them more easily. ZF systems sometimes used more integrated electronic control modules near the oil flow, and if the module overheated, it could change pressure maps subtly and accelerate wear. What are the practical signs to spot during a 10-minute inspection in short drive? First, fluid color and smell. Fresh transmission fluid in these cars is coppery amber. Dark brown or black fluid and a pungent burnt smell point to overheated friction material. Second, magnet inspection in the pan. Some fine metallic dust is normal, but long stringy magnets of metal flakes or nails to the magnet chunks mean components are breaking down. Third, behavior on warm-up. Expect slight slipping during the first cold shifts, but that should vanish once the fluid reaches operating temperature. If slipping persists or the converter feels like it never locks, that's a major red flag. Fourth, shift quality under load. No harsh clunks, no hunt between gears, no high rev standing during acceleration. Fifth, check for leaks and track their source. A minor external leak is often fixable. Internal leaks that cause pressure loss are expensive. If you find problems, there are prioritized, cost-effective fixes that often bring a transmission back to life. The cheapest and most effective first step is a full fluid and filter service with a proper flush and a good OEM equivalent fluid. That restores hydrodynamic film properties and clears varnish. Next, clean or replace the pan magnet and inspect for abnormal debris. Replacing worn clutches is more expensive, but targeted jobs like renewing the pump seals, cooler lines, and torque converter seal can stop progressive damage. Solenoid packs often are salvageable with cleaning or valve body servicing and replacement of a few O-rings. In GM boxes, a pressure regulator valve or sleeve replacement often fixes soft shifts with a fraction of the cost of a full overhaul. In Toyotas, fixing a leaking pan gasket or replacing a worn torque converter lockup solenoid often prevents the need for a rebuild. In ZF units, a careful valve body clean and replacing low-cost solenoids can restore hydraulic fidelity. But if the control module is compromised, expect higher bills.